Hey everybody, welcome back. For the next couple minutes, I'd like to introduce you to something in statistics called regression analysis. Now that sounds really fancy, but I think the intuition is really straightforward, and the computer does all the computational hard work. So it's actually pretty powerful and pretty easy to do. Let's dive right in. So first of all, what is regression analysis? It's really a way for people to examine the correlation between two variables, or even more variables than two. We'll start off today with a simple example of just two variables, and we'll see how variation in one variable is correlated with variation in another. For example, whether you study more or less will determine whether you do better or worse in a class. So study time and grades kind of co-vary together. That really is the bread and butter of statistics, is looking how all these different variables kind of relate to each other. But it really boils down to drawing a line through a scatter plot. There's really nothing more complicated than that. And we're doing that because we'd like to predict some variable y, whatever ultimately that variable is that you care about. Like you want to know, how much do I need to study in order to get a particular grade? The thing you really care about is that grade, and we're going to call that our y variable. So here's a scatter plot. Let's say we were actually looking at house prices. We wanted to know how much a particular house was worth. Now I know that house prices depend on a whole lot of stuff, especially location, but here let's just focus on one variable, square feet. So I have here some actual, some real data, particular houses from where I'm from. And here are the first 5 data points. So we start off with a scatter plot of a particular data set, right? So every particular point represents a particular row in this table of data. And so, for example, we have one house that sold for $72,000. Just hey, it's not bad, but it was a really tiny house. It was 600 square feet. So that's this house right here, 600 square feet for 72,000, right? Below 80,000. And so we just plot all of our data on some kind of graph. And then, we've got tons of data. In fact, the data set I'm pulling from here has, like a couple thousand houses. You can't go through them one by one. You'd like to have like a nice summary of all of the data. Certainly, more than 5 points of data. Otherwise, you don't need fancy statistics for 5 points of data. Extend this data set for all of our observations, 6, 7, all the way down through however many thousands that we have, and we would plot all those points. But ultimately, we'd like to have some kind of summary of what the average price would be given a particular square footage. Now, if we have enough data, we could say, well, maybe the average does something like that. Now, that's a very nice, flexible, functional form. And we'll learn how to do that several lectures from now. But this kind of squiggly line really depends on the particular values of a particular house. In other words, the data might have too much say here. It's also a little bit more difficult to calculate the parameters of a squiggly line. So what we're going to do instead, and what linear regression does really well, is draw a straight line through this scatter of points. So rather than exactly estimating the particular average for every particular possible square foot, we're going to kind of approximate that with a straight line. So something like this. If I can draw a straight line. Maybe something like that is the line that fits that scatter plot the best. That does bring up a question. What do we mean by best? Like, is that blue line that I drew better than this green line? That kind of splits these two observations? I don't really know. Now, I would like to have the best possible guess for how much a particular house would be worth. Maybe I'm putting my house on the market. Maybe I'm trying to buy a house and I want to know how much to bid. So I'd like to get the best possible line through that scatter, which means we kind of need to define what best means. Now, the way that linear regression does this is it keeps in mind the fact that we are trying to predict our y variable. So let's have a candidate line. Let's say it's this one. Of the infinite number of different straight lines we could fit through that cloud of points, let's pick one. And now, if this was, like the true linear relationship between these two variables, then a house of 500 should sell for about, looks like, I don't know, what is that, 85,000 or so. Not 72, but we would have predicted 85,000. This house here was a little higher than we would have predicted. We would have predicted that a house with 116,300 square feet would have sold for something a little bit closer to there. Maybe, I don't know, what is that, 115,000. Actually, if that's 116, then this would be maybe 110 or something like that. So, and so forth, right? And so we would do that for every single one of these data points. We would have the observed value, and we would compare that to what we would have predicted for the thing we are ultimately trying to predict. Right? So measure those differences. We're measuring vertically. Right? And then calculate those differences, as I said. So this would be our residual, which is our observed for a particular value 1 through 5 or 1 through 1,000. So y1, y2, y3. And then what we would have predicted. Let's call that y with a little hat. And had a particular predicted value for the first one, that was 85,000. Y hat 2 was 110, and so forth. We calculate the residuals. That's that difference between what we had observed and what we had predicted. So 72 minus the 85,000 gives us 13,000. And the difference between 116 and 110 is 6,300, and so forth. And the next thing we would do is actually square these residuals. So let's call that e squared. So take all these numbers and square them. I'm not going to do that, but you know how to square numbers. And that's going to be our metric. We're basically going to take all of our errors here, our residuals, we're going to square them, and then add them all up, sum up all of the squared residuals. And we'd like to find some line that minimizes that metric. So let's say we had, a really bad line. Let's say that one right there. Well, then you can see that these errors would be much bigger on average. Oops, here, that one. All the way there and all the way here. And so square those, and we also have a much bigger number. And so we prefer the original green line to the second flat red line, just because the errors are much bigger when we look at the red line. Now you might be wondering, why did we square those distances? There's a couple of different reasons. Let's just say for now that if we hadn't, so squaring them is a way of making these differences positive, so that if we had our regression line and a particular data point, that difference would be kind of the same as this difference. Let's say here to here. Those differences are the same. If we just did y minus y hat, then one of these would be positive, one would be negative, and in fact they'd offset perfectly no matter what the line is. So we definitely need to make these differences positive. And so squaring a negative number makes it positive. So that's one reason why we would do that. You might also take the absolute value. It turns out that's not as good as squaring it. And those details we'll definitely put off for another video. Okay, so let's just take a step back. What have we done? We had a scatter of points. Let's erase all my notes here. We asked the computer of all the different, thousands and thousands of different possible lines, calculate the sum of squared residuals, the squared differences between what we would predict on that line versus our data points. And so pick the best one of all of those, the ones that has the smallest sum of squared residuals. And that's it. That's your regression analysis. Right? Now, no one would want to do this by hand, but thankfully a computer can do it for us. So it's probably a good time to switch over to Excel and show you how it's done in practice. So here we are staring at the larger data set. This is, as I said, it's real data. We're looking at house prices and the square foot. We have here in this spreadsheet 151 observations. The original data set included thousands of these, and these were home prices right after Hurricane Katrina, so which is why they're really low. So Louisiana house prices plus, all these houses are kind of destroyed, but that's not important. Let's do some regression analysis. Now we're going to need the data analysis tool pack. Real quickly, if you don't have that, go into File, Options, Add-ins, and then find the tool pack and install it. I've already installed it, so I'm not going to click OK. Once you've installed it, go to your Data tab, and then you should see Data Analysis all the way to the right. So we click on that. Okay, so here we've got all these different cool things that Excel can do with statistics. And we're looking for regression, which is right there. Click OK. So now we just key in our data. Let's make sure that our mouse is, our cursor is in that little window for the Y range. And now we just specify the Y range. So we're just going to highlight that. We go all the way down to 151. We do the same thing for our X variable. We start at the top and highlight down. Now our very first cell was, row 1 was price and size, I think it was. So we just want to tell Excel, hey, that's not data. That's a label. You can ignore that first row. And then we can just get our regression output. There's definitely some interesting options here. We're not going to get into those now. So let's put our cursor right there into that window and specify where Excel should put all of its output. And we can minimize that and then say let's do it in cell, not D126. Let's go all the way up here. Let's start at D1. Open that up and then click OK. And just like that, you actually have all of the information that you wanted and a whole lot more. So this is kind of daunting, maybe overwhelming. For now, there's only a couple of things that are crucially important. And the first thing is we want to know what was that line in the first place? What was the equation that Excel estimated? Now remember that when you're trying to estimate a line, there's two parameters. There's the slope and the intercept. That's what we want. And that's what these two numbers are right here. You're going to find those under what's called coefficients. The intercept is clearly the intercept. And then our X variable was home size. And so this is the coefficient that's associated with home size. So that's our slope. So that's what we need. Okay, so the equation of a line is y is equal to mx plus b. We've got the slope, and we have an intercept. And that's the information that Excel gave us. We had a slope estimate of 49.37 and an intercept of 63.7 45. Let's verify that real quick. Here's our Excel data. Sure enough, we had an intercept of 63,745 and a slope of 49. All right, so house prices are equal to, and then we can just rearrange these. It's usual in regression analysis to put your intercept first. Plus $49 for every square foot, which is nice and cheap. But again, you got to realize these are beat up houses. But there you go. You now have estimated a line that fits a scatter of 150 home prices, and it fits it the best of all possible other straight lines someone might draw by hand or by using any other means at all. Right? So this thing that Excel spits out is the best fitting line possible, which is really neat. And this is a nice summary of 151 rows of data with 2 columns each. So now if someone said, you know, I think I want to sell a 1,000 square foot house. What should that house sell for? Well, then you would plug in 1,000 in for square feet. Plug that in right there. Multiply that by 49.37. Add 63,745. And you would get your estimated price. I'm curious now what that is, so I'm going to calculate it, which is that cell right there, plus 49.37 times the number of square feet. We said that was 1,000 square feet. So we would expect this price for that home. Let's add some formatting. So it should sell for $113,120. If you can find it for less than that, great, you're getting a deal. If someone is listing it for more than that, they're asking too much, and you should pass on that house or at least make them a lowball offer. But this is a nice way of seeing whether a house is over or underpriced. And that's kind of the power of regression analysis. So just a little bit of advice about interpreting all of that Excel output. The 2 key things for us were the intercept and the slope, the coefficient that's attached to our x variable, square feet in our example. Now, you're facing these, numbers, and you got these equations of lines, and really you should kind of take pains to translate this from like math stats speak to something a little bit more human. So let's think about what these parameters actually mean, like English. Well, let's think about what the intercept is saying. We've got that line. We've got some scatter of points that go around that line. Here's our square feet, and this was price. The intercept is that point right there. Essentially, what that intercept says is, if someone was trying to sell you a house with 0 square feet, in other words, an empty lot, then that's the price it would fetch. So your intercept is the expected value of y, whenever x is equal to 0. Now I should say right now that if your data set does not include any empty lots, any observations where your x variable, whatever it may be, is actually 0, then don't put any stock into the particular value about what a means. Just ignore it, because you're on statistical thin ice. You're projecting where you don't have any data. If your data stops here, you got tons of data, you're skating on thin ice right here. Right? You're presuming that the world continues linearly. You really don't have any data to support that kind of assumption. It could be that it does this. And so since you don't know that, don't put too much stock in the intercept unless you do have observations around that point. In other words, in our example, if you do have homes with no square footage, in other words, if you have empty lots in your data set. Now, the other variable or coefficient that you're looking at is the slope, what's often in statistics called your beta. Okay, and that is your slope. And just like any other slope, a slope is rise over run. In other words, it's the change in the y direction divided by the change in the x direction. Our y variable was price, so it is the change in price divided by the change in square foot. All right, so put that all together, and what this means is the slope tells you how much your price will change for every 1 square foot change that you could, think up. All right, so if you were going to say, I wonder how much a particular price would sell for if the square footage was 100 more, then you would have slope change in price over 100 more. And so what was our slope? I think our slope was 49. So 49 is equal to change in price over 100. We would cross multiply, and so the change in price would be 4,900. So you would expect that your price would be higher by 4,900. Right? The critical part here is that the slope is equal to the change in price divided by the change in square feet. Change in y over change in x. So whatever your x might be, it might not be square feet when you do your regression analysis, but it is how much y changes for every 1 unit change in x. And then you could maybe even hypothesize more than 1 unit just by plugging in your values into that formula. So that's it. That's kind of like the nuts and bolts of that statistical output. Now, all of that information that Excel spit out, there was tons of it, all of that is useful. And so as you're diving into regression analysis, you'll learn more about what all of those numbers might mean and how they could be like warning signs that something might not quite be right. But we'll get to that. Now, usually at this point, your job isn't done. You see, you don't have the entire population of data. You took a sample and used that sample to kind of guess at what the population truth might be. And so you always have to do hypothesis tests to see, is what you estimated like kind of robust? Could it have been 0? So Excel shows you part of that, and I'll just bring that up real quick. So we got Excel up again. Let's focus on one particular part. So we've estimated 2 parameters, the slope and the intercept. Slope, intercept. Let's clean that up a little bit. Let's get rid of some of those decimals. We don't need those decimals. Now, anytime you're doing a hypothesis test for an average, you either looked at the critical values versus your test statistics, or you looked at the p-value. All right, now, how do you calculate those critical values? You need standard errors. The implicit hypothesized value for all of the estimated coefficients is 0. So your test statistic is your estimate minus 0 divided by the standard error. And so if you were to take 63,745 minus 0 and then divide by the standard error, you would get this test statistic, 797. So that's very far away from any of the critical values you would normally deal with. You would be looking at around 1.96 for your critical value. So this test statistic is way bigger than that, and so is the one for your slope. You also know that you would reject the null if your p-value is below the significance level, that alpha value, which was usually 5%. And here you've got a 0 point, and then you got like 13 zeros. It's way below 5%. So we would also reject the null by looking at the p-value. And then one final way of doing a hypothesis test is by looking at your confidence intervals. So let's get rid of some of these decimals too, just to make it more readable, is between 47,000 and 79,000. So those are kind of like your plausible estimates for what the intercept might be. And 0 is not one of those plausible estimates. So your intercept is not 0. What about for slope? Now our slope was 49. That was our estimate. But this was a sample. It could have been a little bit above, could have been a little below, just from random chance. So if we try to account for that random chance, our confidence interval at 95% is between 41 and 58. And our estimate of 49 is smack dab in the middle of those two numbers. So we think, it could have been as high as 58, it could have been as low as 41. Our best guess is 49. But notice, we could go as low as 41. We can't go as low as 0. Right? So 0 isn't a plausible estimate. And so we would toss out that hypothesis as well, that the slope is 0. Or to put it in more human terms, we've just eliminated the hypothesis that square footage and house prices aren't related. Of course they're related, but now we have statistical proof for that. There's tons more to do with regression analysis. You could spend your entire lifetime studying and learning more and more about regression analysis. But we don't have time for that. I should shut off right now, and you should go do some homework. Catch you next time. Bye.